In the last section, we discussed intermolecular forces and differences in their strengths. Now, that doesn't necessarily mean a lot to us unless we can actually apply it to something that we can observe. And so in this video, I'm actually going to talk about how the strength of intermolecular forces affects 3 different properties of liquids. The first one is boiling point. Now, to understand boiling point, I also have to talk about vapor pressure. Vapor pressure is the pressure that is exerted by a vapor. So it's the pressure that results when a liquid becomes a gas, and it's that pressure that results from the gas. And so as you can see right here, I have a liquid and I have vapor. I have gaseous water that is leaving the liquid water. Now, the pressure that's exerted by this vapor, that is your vapor pressure, and boiling occurs when that vapor pressure equals the atmospheric pressure outside of that container. Now, the important thing for you to know about boiling point is that if you have molecules in that liquid form that have very large intermolecular forces, meaning they're extremely attracted to one another, in order to get to your boiling point, to the point at which the vapor pressure equals the atmospheric pressure, you're going to have to apply much more heat, and therefore the boiling point is going to be much higher. So for example, water, which has strong hydrogen bonding for its intermolecular forces, water has a very high boiling point. It has a boiling point of 100 degrees Celsius. If you looked at other substances, for example, alcohol or certain oils, their boiling points are much lower than that of water. And the reason why is because of intermolecular forces. Water has a very strong hydrogen bonding and therefore has a much higher boiling point. The second characteristic that we're going to look at is surface tension. Now, surface tension, you've heard that term, but to better understand it, you need an official definition. And the official definition is the tendency of liquids to acquire the lowest surface area. So I'm going to explain why they want to acquire the lowest surface area, and then I'm going to show you how you actually experience this every single day. If you look at this diagram right here, which came from your textbook, the reason why liquids want to acquire the lowest surface area is if you look at the molecules at the surface of this, if you notice, they're attracted to other molecules to their left, to their right, below them, to the left, and below them to the right. There's nothing up above them. And so as a result, those molecules are experiencing a downwards force, and therefore there's this downward pull on them, and they try to minimize their surface area. Now, if you notice the molecules within the substance, they have an equal pull up, down, and to either side all around, and therefore they do not feel that net inward pull, and therefore they don't have a tendency to acquire the lowest surface area. So it's just the ones on the surface that are trying to minimize their surface area because of this net force downwards. And so where you see surface tension, if you've ever tried to add drops of water to a penny, which I do with my Gen Chem kids and with biology, if you try and drop water onto a penny, you'll create this awesome bulge on top of the penny. And the reason why this occurs is because of that pull for those water molecules towards the center of that droplet. Now, if you did the exact same thing with oil, for example, you won't get as bulbous of a droplet. And the reason why you get this with water, and you can fit more drops of water onto the penny, when you compare that with oil you can't fit as many. The reason why is because water has very strong intermolecular forces. It has hydrogen bonding, while oil has dispersion forces. If you did it with vinegar, for example, you would have dipole-dipole forces. So the strength of the intermolecular force actually dictates specific characteristics, such as surface tension. The last characteristic that I'm going to talk about is capillary action. Now, you should have heard about capillary action in your biology class. That is the ability of roots to take water up them and go against gravity. Another case is if you take a really thin straw, water will move up it. In order to understand capillary action, though, you need to understand two characteristics. The first one is cohesion. Now, cohesion is the intermolecular force between similar molecules, and adhesion is the intermolecular force between a molecule and another surface. So as you can see here, this is a great explanation of these two phenomena at work. If you look at water, notice you have a concave surface. That's the meniscus that you've learned how to read. The reason why that forms is that the adhesive forces between the water and the glass are actually stronger than the cohesive forces between water molecules, and therefore the water is attaching to the sides of the glass test tube. In contrast, for mercury, mercury has stronger cohesive forces, and as a result there's that convex shape. The reason why mercury has stronger cohesive forces, if you think about it, mercury is a metal, and therefore the attractive force that's holding the mercury atoms together is actually an intramolecular force that's metallic bonding. And so obviously that's going to be stronger than any type of intermolecular force. So those are the three characteristics for liquids that we're going to study.